In this section, we're talking about density functions, expectations, and general integrals. To start, let's consider the density function as defined in measure-theoretic terms. Let's have two measures, mu and lambda, both measures on a measurable space. Let's also consider a function little f, that is from the outcome set to the non-negative real line. Now, if it's the case that for all sets in our sigma algebra, the measure mu of that set is equal to the integral over that set of the function f times the measure, lambda, then f, little f, is called the density of mu with respect to lambda. Now notice in this case that this is not restricted to probability measures. It's just simply two measures, mu and lambda. And our use of this, mu is typically taken to be a probability measure. Lambda is typically taken to be the Lebesgue measure. If my handwriting on this pad looked any bit legible, you'd see that says somewhat Lebesgue. But in any case, if now the set A is a set in the finest partition of the sigma algebra, which is to say that there are no subsets of A in the partition, in the sigma algebra rather, then the measure mu of A, being the integral over that set A, is actually defined by our definition of integral that we have described before. Simply the value of the function at omega that gives us the smallest value times the measure lambda of the set A. Moreover, if A is a singleton, which means it only has one point in it, then it simply reduces to mu is equal to f at that point w times lambda of A. And we get simple equivalence of the integral of some function g of x times the measure mu is equal to the integral of g of x times fx times the measure lambda. And f becomes our density for mu with respect to lambda. In terms of the Riemann integral, we can consider that our density, little f, is defined as the limit of the CDF evaluated at x plus delta minus the CDF at x divided by delta. And that gives us the df, CDF, dx. And that implies then, if we were to solve this simply, that the differential in f is equal to the density times the differential in x. And so we plug that in. We've got our df is equal to little f dx, and we can equivalently write our integrals either way in the Riemann sense. So let's consider the definition of expectations. We have a measure space based on some probability defined in accordance with however we're using this. Most likely in our cases it'll be a probability defined on a data generating process. So it's trying to describe the uncertainty in what the data generating process could produce. We have random variables x, which map to then another measurable space and gives us a measure space associated specifically with x, probability associated then with x, and from this we get our CDF and our PDF. Well, we can write the expectation of x along multiple different ways depending on the different measures or functions that we use. So for example, in the original we can go back to the random variable x as a function of omega times the probability, and this probability is the original probability space. And you would integrate that across the outcome set, and this would give the expectation of x. Similarly, you can use the space on the range side of our random variable here, and we can take the value of x times the probability and integrate this across the real line, or we can express it in terms of a Riemann integral, taking x from negative infinity to infinity, x times d the CDF, which we can also then express in terms of simply dx, being negative infinity to infinity x the density dx. All of these would give you an expectation. Now here it was just the expected value of x. We can substitute in essentially any g of x for x, and that would give us the expected value of that function of x. So it's fairly general. As an example, let's suppose we want to integrate this function here over the range 4.5 to infinity with respect to lambda, which is our Lebesgue measure. Now let's use a strategy that we've done before. We want to transform using a variable on the unit interval. So we have x is equal to 4.5 minus log u. You can see this being the case because as you vary log u, or vary u, 4.5 minus the log u will give you the range of x that we're looking at. And therefore u is equal to e to the 4.5 minus x, and dx du is equal to negative 1 over u. Now let me define c sub x as being an infinitesimal set in x, and c sub u being an infinitesimal set in u. The measure, the Lebesgue measure, of our infinitesimal set of x is going to be the determinant of the derivative of x with respect to u times the lambda cu. And so we get, well actually, in this case, this is actually the absolute value. This sign here, I should have used a different sign. It's the absolute value of dx du times lambda cu. So we get the absolute value of dx du times the absolute value of du. So our integral becomes an integral from e to the 4.5 minus log u again. Put it up there, and down here it's e 4.5 minus 4.5. Which we can transfer over to be, this is minus infinity. This is minus 4.5, so we end up with integral from 0 to 1 of our function times the absolute value of the derivative with respect now to the measure lambda. And now we're taking it over the range of u, so we're looking at sets defined by infinitesimals, sets of u. Now notice that for u having a uniform distribution, as if it were a random variable, the probability is simply 1 times lambda. In other words, the density for a uniform distribution is 1, the constant 1. Which also means that I can take my lambda, this lambda, which is the same thing as 1 times lambda, right? That's just a simple representation, which is the same thing as pu. So the probability pu sits here. And what does that say? That says that really I am taking an expected value of this function capital G of u, which includes my derivative there, with respect to a random variable u. So basically we have the expected value with respect to the variable u of G of u. And that gives us that integral. Up to this point, you will notice that I didn't actually state at the very beginning that I was considering this function as anything to do with random variables. It's just an integral that I want to do. But I convert it into an expectation. And an expected value of some function is easily estimated, we do it all the time, by a sample average. If I could draw a random sample of u and get a sample average of the GUs, I would have an unbiased estimate of the expected value of GU. That will be the basis for Monte Carlo integration, even when what we're originally integrating is not at all related to any concepts of probability. But the concept of expected value under the unit interval will become key to getting numeric estimates of integrals, even if the integral itself is not motivated by any sense of probability. So how do we estimate this? Well, as I said, the sample average of a random sample from u, in this case being uniform because that's what I created above, would give us an unbiased estimator. So what that means is I would draw a sample of capital R number of values of the uniform distribution. I would calculate that function g at each of those values, and I would take the sample average. This is an estimate of that original integral. Now to do that, we had converted this to a unit interval. Don't necessarily have to do that. We could also observe that our original integral happened to be a density for a standard normal distribution. So that this integral is the same thing as integral 4.5 to infinity under P, where P is a probability measure associated with a standard normal distribution. Therefore, I could actually look at the integral across the full real line of an indicator function of values that fall within the range of 4.5 to infinity. In other words, I can take the expected value of an indicator. How would I do that? Well, I would draw a sample now from a standard normal, not a uniform, but a standard normal, and I would create a variable that's an indicator whether that draw fell within the 4.5 to infinity range, and I would take the sample average, which is the proportion of them that falls within that range, and that would be my estimate of this integral, which in fact is the probability under the standard normal of being in greater than 4.5. So both of those would be a way to use a Monte Carlo strategy, drawing randomly from a distribution to calculate an integral. Now let's think of the general integral. So with a general integral, let's think of x as a vector of values and u as a vector of values. And my dx1 times dx2 all the way up to dxk, let's say that's a k-dimensional vector. Think of that as a volume of an infinitesimal hypercube. Again, we'll call that cx. And du1 times du2 times all the way up to duk is the same thing, the volume of an infinitesimal hypercube cu. So if I can express x as a function of u, this is a vector valued function, then I can get my derivative of x with respect to the vector u as a matrix. That is this matrix here. So it's the partial derivative of x1 with respect to u1. Keep that out to xk with respect to u1. And keep that going all the way through each of these rows until you get the derivative of xk with respect to u1, uk. Excuse me. Let's rewrite this, x1 with respect to uk and xk with respect to uk. And this will give you a matrix of derivatives. Now, the measure lambda or volume, so to speak, of this hypercube in terms of x is going to be proportionate to the measure of the hypercube in terms of u, and the proportionality factor is going to be the determinant of this matrix and then take its absolute value. So the absolute value of the determinant of our matrix of derivatives times lambda of the infinitesimal hypercube in terms of u. So this becomes my rescaling factor, similar to the univariate case where we took the absolute value of the derivative just by itself. In this case, it's the absolute value of the determinant of the matrix of derivatives. So my integral of gx in terms of lambda can be expressed as the integral of gx as a function of u with respect to the absolute value of the determinant of the derivatives, and lambda is now applied to the space defined by u rather than x. Notice that all of this up to lambda we will call capital G of u. Lambda is again just 1 times lambda, but since we're looking at uniform distributions, because my u here is uniformly distributed, it is a multivariate uniform distribution for u. And I therefore have the expected value under u of G of u. So in a general sense, we can take a very general integral that we were interested in, which would be this integral of g of x, or g as a function of x, times lambda. We can convert it to a function of unit interval variables and use our same, as we've done before, our rescaling. Plug that in. So it's the function originally as we had it, only now it is evaluated basically at u. This x of u means that it's going to go in there actually as a function of u. Multiply it by that scaling factor, which is the absolute value of the determinant of the dx du, times lambda, where this lambda again is associated now with a partition related to u rather than x. And we end up with, again, our expected value. The original integral, again, doesn't have to have anything to do with probabilities. It can just be an integral in multivariate space. And if you convert it to a function of unit interval variables, you can express it as an expected value in terms of a distribution on multivariate unit intervals, uniform distributions. So this ends this section of the lecture.